Good morning, champs. Today, we're building a complete solution strategy for one of the most important laminar flow problems in fluid mechanics: steady flow between two infinite parallel plates. This is not about memorizing a velocity profile. It's about knowing exactly what to do when you see this geometry, every single time. We start exactly the same way as for pipe flow, with a control volume and a force balance. The geometry is simple: two large parallel plates separated by a distance 2h. The flow is fully developed, steady, and in the x direction. The velocity depends only on the transverse coordinate y. There is no acceleration in time and no velocity variation along x. Now define the differential control volume. Take a small rectangular fluid element of length dx, width dy, and unit depth into the page. Flow is in the x direction. Y is the direction where shear stresses vary. That choice is crucial. Next step: force balance in the x direction. No assumptions about the fluid yet, just physics. There are three contributions: pressure forces acting on the faces at x and x plus dx, shear stresses acting on the top and bottom faces at y and y plus dy. Gravity does not contribute in x, so we ignore it here. Write the pressure force difference. Expand the pressure at x plus dx using a Taylor expansion. Then write the shear force difference using the shear stress gradient in y. Set the sum of forces equal to 0, because the flow is fully developed and acceleration is 0. After simplifying and dividing by the volume, we obtain the governing equation. Now we integrate with respect to y. Integrating once gives the shear stress distribution. Tau equals dp over dx times y plus constant c1. Next, we bring in the fluid model. There are many possibilities here: Newtonian fluids, Bingham plastics, power law fluids. In this video, we use a Newtonian fluid because it is the most common and the most important. For a Newtonian fluid, shear stress is proportional to the velocity gradient. Tau equals viscosity times du over dy. Now apply boundary conditions. First, symmetry. The center line between the plates is at y equals 0, and the shear stress there must be 0. That immediately eliminates the first constant. Second boundary condition: no slip at the walls. At y equals plus h and y equals minus h, the velocity is 0. Applying these conditions leads to the final velocity profile. This is the classic parabolic velocity profile for laminar flow between parallel plates. Maximum velocity occurs at the center line, velocity goes to 0 at the walls, and the curvature is set entirely by the pressure gradient and the viscosity. Pause here and reflect. The solution strategy matters more than the formula. Control volume, force balance, constitutive law, boundary conditions. Geometry only enters through those boundary conditions. Once you master this workflow, you can solve variations effortlessly: one moving plate instead of two fixed ones, one plate only, inclined plates with gravity included, different fluid models, same steps, same logic, same confidence. That's the goal. One geometry, one method, infinite applications. All right, champs. That's laminar flow between parallel plates done properly.